Hello, everybody. Welcome back to Planet X News. This is Scott from the Nibiru channel. Excuse me. I have Chris Potter and our physicist here, and we're going to be talking about why the Earth's mantle is heating up, the increased internal temperature. So, Doctor, how are you this afternoon?
I'm very well, thank you, Scott. And how are you?
I'm doing pretty good. Christopher, how about yourself?
I'm doing great. How are you?
I'm not doing too bad. The temperatures are 81 degrees here. The chemtrails are out. They're blocking out the sun. Just absolutely incredible what they do. As soon as the blue sky appears, the chemtrail planes are out there like little spaceships, mucking up the sky. Makes you wonder. But anyways, ladies and gentlemen, we're going to be getting into an article, and the article that the doctor wrote is concerning the internal temperature increase in the Earth's mantle, and it is due to the presence of a brown dwarf star in the solar system. And this was dated just a few days ago, and she's been doing some absolutely incredible work. And over the course of the next several days, we're going to be having some groundbreaking information. We're still actually working on it at the moment, and we could have it back to all of you as early as tomorrow, possibly Wednesday. So definitely stay tuned. So, Doctor, you want to go into this very, very impressive report that you've established here. I was reading over it earlier, and this will definitely be something that you will have to explain. So I will give you the floor.
Okay, thank you, Scott. Well, it's actually a very simple model. I use very simple mathematics. I know it looks complicated to you, but I'm just using pencil and paper methods. In other words, I didn't use any computer modeling to do this. I just I make a few assumptions, which I think maybe I should talk about.
Why are assumptions important?
Well, you always start out a model by, you have to make assumptions because the model has to be simplified. It's not a real world model. I mean, the model models the real world, but it's never the real world because there are too many variables in the real world. So as far as I'm concerned, I like to start out by simplifying things as much as possible. I know that nowadays physicists like to make things a bit more complicated than I think they should be. And I mean, it's come to the point that, you know, people think that physics is good because it's very complicated. But I think you only need to complicate it more if the first result is not good enough. So you should make it as simple as possible, at least at the first attempt. So this to me is a simple model that I just wanted to see if I could get, if I put a brown dwarf star with a kind of a standard size and the standard magnetic field at a distance which is like halfway between the sun and the Earth, which is a kind of a standard for me distance. So that's the first assumption, that first of all there are brown dwarf stars in the solar system. Well, to me it's not that much of an assumption, but you know, I know that they are there and that they are in the inner solar system. So basically I assumed a distance that is reasonable to me. Okay, so you always try to make an intelligent assumptions. So I start out by explaining that brown dwarf stars come from white dwarf stars. They just cool down white dwarf stars. So they don't emit much visible light, which means they will have a surface temperature of about 1,000 Kelvin or less. So it takes a while for a white dwarf star to cool down to a brown dwarf star. But that's not what's important here. What's important is that they have very high magnetic fields. Because when white dwarf stars form, they collapse into a much smaller size. So they can go from being the size of the sun to being the size of the Earth. At least that's theoretically what's been decided. I'm not completely sure about that, but I'm using the standard astrophysical theory on that. So I'm taking a standard white dwarf that has cooled down to become a brown dwarf. So it's about the same size as a white dwarf, which is about the same size as the Earth, if the star initially was about the same size as the sun. Okay, so those are my initial assumptions. Okay, if you can scroll down a bit further, we can get into what I say after
You
that.
can scroll down a little further.
No, I think
Yeah,
that's
please, Scott.
Oh, okay. Well, I'm going to interrupt a little
Okay.
bit.
Yeah.
When you mention its magnetic field, and you mentioned the size, for example, the size of an Earth, is the mass increase on a star that goes from a, white dwarf
Yeah,
to a brown
well,
dwarf?
actually,
Is that a given, or go ahead?
no, it doesn't actually lose much mass, but what happens is it becomes extremely dense, okay. Because it basically, well, the theory is that gravitational collapse, once the nuclear reactions have stopped, it collapses due to gravitational attraction towards the center, so it becomes very dense. Okay, my own observations have led to me to believe that what happens might be different from that, but I'm just using the standard theory here. So basically, the gravitational attraction causes it to collapse into a much smaller, much denser object than it was, especially in the red giant phase, where the outer layers are very diffuse and it's a very large star. So, but basically, it's very dense, but it doesn't lose much mass. I mean, it does lose its outer layers of gas, but most of the mass would still be there that it had when it ran out of fuel. And it can be different cores. So depending on what kind of fuel the star was able to burn, if it was able to burn right up to iron, it becomes an iron core brown dwarf star, which is denser than the helium core brown dwarf star.
When you had mentioned that it had been denser, I apologize for interrupting. When you had mentioned that it was denser, my automatic assumption was that the mass was greater or would be greater. And it was interesting that you even mentioned that it didn't lose mass, which was completely the opposite of what I was thinking. So I appreciate you verifying that. Are we going to go from equation 1, or is this where you wanted to start presenting?
I think we should look at equation 1 first.
Okay, yeah.
And actually above that, because, there I explained that when the star collapses into a much smaller size, it rotates faster, and that's to do with conservation of angular momentum. You know, like a skater, if you've ever seen skaters do that, their spins, and they usually have their arms out and they curl them in, and that causes them to spin even faster. Okay, so
on roller skates or rollerblades. Yeah, I gotcha.
Rollerblades or ice skating is the same thing. So if you large, that is, your arms are out, then you will spin slower than if you bring your arms in. You will spin faster. So that means that as the star collapses, its size decreases, so it spins faster. Okay, just like the ice skater. So as it collapses by a factor of 100, it spins at a square of that, because that's what the relationship with angular momentum. That's why if it initially had a magnetic field of 100 Gauss, it ends up with a magnetic field which is 100 squared times 100 Gauss, which is 1 million Gauss.
Wow.
So that, so it increases a lot, the magnetic field, when these stars form, when white dwarf stars form. And basically, brown dwarf stars will have the same magnetic field. There is a bit of a decrease with time, but I didn't go into that. So again, there is another assumption. I assume there's no decrease in the magnetic field. And obviously, I ignored that. There should be a certain decrease, but I ignored that. But I started out with a standard magnetic field of 100 Gauss. And I mixed white dwarf stars with much larger magnetic fields, like 1,000 times larger than the standard magnetic field. In Tesla, it's 100 Tesla. Okay, now our sun actually
magnetic field is going to absolutely have an effect on any body that it's close to, and because that goes back into your analogy of the strong force, where it attracts one another.
Yeah, I don't go into the strong force here. I just use the magnetic field.
I know that, but I was just kind of stepping into that.
Yeah.
that for me visually, I could understand immediately the natural fluid, what am I trying to say? That was just the next naturally occurring thing to my mind because of the papers that you've put out. That was the first thing I thought. I can't word my freaking thoughts correctly. So I hope you understand. Sorry.
Yeah, no, I do understand that we have to go into the strong force when we realize that there are stars being attracted to the sun. But in this model, I don't mention that at all. I just deal with the magnetic field and the effect it will have on the Earth by heating up the Earth's core, okay?
Perfect.
So I just wanted to have an idea of what effect the standard kind of brown dwarf star would have on the Earth's mantle, how much of a temperature increase it would create. So that's what you do when you model. You know, you forget about all the other stuff. You focus on one thing. And here I focus on the magnetic field and its effect on the Earth. So then I have to have a magnetic field that changes. And I just say, well, it changes because the brown dwarf star is rotating. And as we know, brown dwarf stars rotate much faster than larger stars for the same reason that the skater spins faster as it decreases in size. So that's to do with angular momentum. So I just give it a simple magnetic field with a periodic change given by the cos function. So I say, well, the magnetic field changes with time. It's got B is the constant strength. C naught is what I'm going to use to vary it with distance. And then the cos of omega t is how it varies with time, and it's periodic because the cos function is like a wave function. It goes up, comes down to the middle, keeps going down, you know, like a wave on the sea. So the C naught is the parameter that takes the distance between the brown dwarf and the Earth into account. And the magnetic field is just 100 Tesla, which I calculated initially that a standard brown dwarf star would have. Omega is the angular velocity or angular frequency of the star's rotation, and that's associated to a period of 27 hours because I saw there was a brown dwarf star in the Secchi images, and I calculated that its period was about 27 hours by observing how it takes about 27 hours to come back to the same configuration. So I use that here. From that, I calculate the omega, which I need in the B function. So that's the 2 pi over t. The t is 27 hours. So when I calculate...
We need to go back to equation 1.
Okay.
Yeah, scroll up to back to 1. Aren't you explaining equation 1?
Yeah, I was, but it's okay.
Oh, I thought you were actually going to repeat the actual equation itself. You're just kind of giving a...
okay, I can.
Well, please do that, because I thought that was extremely important. The mathematical side of your presentations, because I don't see anybody else out there making any mathematical equations of any type in this regard, and I want to just have you emphasize that. Thank you. I'll be quiet now.
Oh, okay. That's okay. Thanks for the questions, Chris. All right. So, Scott, you need to scroll up a little bit more so I can look at the equation 1. Okay. There we
it's
are.
at the bottom. It'll be a number 1 on the right instead of the left.
Just jumps about.
She put the going down. There you go. It's right there. It's at the very bottom.
There we are. Okay. So B is the constant. It's 100 Tesla. C naught is to take into account. It's a parameter to take into account the distance between the brown dwarf star and the Earth. The cos function is a wave function that makes it vary periodically. Okay?
A cosine, right? Cosine?
It's the cosine function, yes. Okay, and the omega...
C naught is the C and the little 0.
Yeah, that's the C naught.
Right. The reason I'm saying this is because I have no friggin' idea what I was looking at. And you actually had to write the equations out for me. And that's how I'm able to present the material. And I'm not afraid to admit that. So I wanted to actually understand what you were saying and how you were reading it. So cosine, and then that next symbol is the omega symbol, right?
Yes.
Is it? That's from Latin? Or is it from Greek?
That's Greek. Yeah, it's a Greek letter. Yeah.
In physics, you guys use a lot of Greek symbols in physics?
Yeah.
Okay, so I had no idea, and that's why I asked. Thank you for explaining that. And then T Is
And
what you
T-
were mentioning is Tesla. No?
No. That's the small t, and
That's
it
lowercase
represents
t.
time.
Ah,
So
that's what it was.
it's measured in time units like seconds or days or hours or light years. Usually we use seconds.
Okay.
Okay, the capital T is the unit, the standard unit for magnetic fields. That's the Tesla.
Awesome.
But some people prefer to use the Gauss, but we usually convert from Gauss to Tesla because Tesla is the standard unit. Okay.
Gotcha.
So basically, that's the equation. So now we can go down to equation 2. Okay, so that gives you how I calculate the angular frequency. The angular frequency is the number of radians in a circle, which is 2 pi, divided by the period of the star, which is 27 hours. And then that's written in terms of radians per second. That's the standard unit for angular velocity. Okay, so that I will just plug into the equation at the end. So I just wanted to calculate what that was. And then I looked at what to do with C naught, and I made it so that the magnetic field decreases as a 1 over r squared. That's the standard way. Well, magnetic fields can decrease as 1 over r squared or over 1 over r. If they decrease over 1 over r squared, they decrease much faster than the 1 over r. And the 1 over r squared decrease is called the inverse square law. A lot of forces and interactions in the universe seem to decrease at that rate. So it's a standard way of making forces decrease. So then R naught is just a constant. It's just there to keep the units correct. So it's got the unit of meters. And then the little r is about half the distance between the Earth and the Sun. The distance is 14.5 times 10 to the 7 kilometers, or 145 million kilometers. So I just made it 70 million, or 7 times 10 to the 7 kilometers.
Oh, okay. Go back up for a second, Scott, for me. Thanks. On 2, I have to ask you 2 questions.
Okay.
You have to please explain what radian is and what angular frequency is.
All right. So we usually measure angles in degrees, and we know they are 360 degrees in a circle. Okay, so we all know that. But we can also measure it in terms of radians, where we use the fact that the circumference of a circle is 2 pi r, 2 pi times r. Okay, and then another way of measuring angle is to just make the angle equal to the arc length, which is a portion of the circumference of the circle, divided by the radius of the circle. So a 360-degree angle is equivalent to the full circumference of the circle, which is 2 pi r, by the radius of the circle, which is r. And if you can picture that, you have 2 pi times r divided by r gives you just 2 pi. So that means 360 degrees is equal to 2 pi. But that it is now measured in another unit, which we now call radians.
Yes.
Okay, so 360 degrees is equal to 2 pi radians. So 180 degrees is a half of 360 is equal to pi radians. Okay, so that's how we can convert from one to the other. And the radians are useful because if the angle is small, we can substitute the sine function, sine of theta. If theta is in radians, we can just use theta instead of sine theta.
Theta, so that's how you say it, theta, not theta. Okay.
Yeah. Oh, you can use theta as well.
Oh, okay, okay.
I usually.
Interesting.
So
I'm following you, actually. So a radian is a unit of measure.
Yeah, it's a unit for measuring angles. It's a different unit from degrees, that's all.
Well, thank you for explaining it. Okay, so this particular number 2, equation 2, can you explain or read it actually?
All right, so we usually have velocity, which is a distance divided by time. And then it would be measured in meters per second, right? But now omega is, well, here I call it angular frequency, but it's also called angular velocity. Okay, it's the same thing.
Gotcha. Okay.
Angular velocity then is an angle divided by a time instead of a distance divided by a time.
Mhm.
Okay, so that's the difference between angular velocity and velocity. Notice we use the omega. The omega looks like two V's together.
Mhm.
Okay? And we usually use the symbol V for velocity, and then we use the symbol omega, which is a little similar to V, for angular velocity. Okay, so that's why the units are now radians per second, whilst for velocity will be meters per second. That's the only difference. Okay.
All right. I guess it's easier to be able to calculate out your equation when you have to use different measurements like that. For example, using radians, etc.
Yeah, you see, because angular velocity and angular frequency is the same. And
Oh, okay.
an object that is moving around in an orbit, it will get back to the same position in the time. For this one, it's 27 hours. It means that it's going around at a certain rate, which is called the frequency. Okay, so at every 27 hours, it makes one orbit. And so the fact that it takes 27 hours means it repeats the motion with a certain frequency every time, and we can calculate that frequency. And then when we say angular frequency, it means we're measuring the frequency in terms of radians. Every time we use angular, we mean radians is the measure, is the unit being used.
That's what I was trying to say. Thank you.
Yeah, okay. All right, so then equation 3 is the C naught, which I just trying to make sure that I account for the fact that the brown dwarf star is not right on top of the Earth. It's at a certain distance away. So trying to make it a standard distance.
C naught is equal to R naught over R all squared, and it's lowercase r. Because the...
Yeah, I used the low... Yeah.
You were just going to say what I was... Go ahead. I was just going to ask
Okay, the little r is usually used as a variable. In other words,
Yes.
I could have varied it to any distance I want. And in fact, I could in the end, because I want to put in the r towards the end of the equation. But I just say right at the beginning that I'm going to assume that it's 7 times 10 to the 7 kilometers. So I'm making the assumption right at the beginning. I'm not leaving it open. But I could have left it open, or I could go back and recalculate for different distances. For example, I could make it, instead of 7 times 10 to the 7, I could make it 3 times 5 times 10 to the 7. And the equation will then give me the temperature increase for that distance. Okay, so a variable means it can vary. So we usually use the smaller case r to mean it's something that we can vary in the equation.
It's like a placeholder. I remember from just basic algebra that a variable was like a placeholder.
That's right. Whilst the r naught is just a constant, I set it equal to 1 meter, and it's going to stay like that. Okay. So that's equation 3, and then we have figure 2, where I show the different layers we have inside the Earth. So there's the solid core, and the fluid core, and the mantle, and I basically assume that the induced current will be in the fluid core. Okay, I could have done it differently. I could have assumed that it was in the solid iron core. But I decided to put it in the fluid core because it's the larger radius. So it will have the larger effect if I put it right on the outside of the fluid core. Okay, so that again is another assumption that I made, where to put the induced current. All right,
and
but
so this paper is specific to why the magnetic field of the brown dwarf affects the Earth's mantle. So that was why you were very specific. That was the exact nature of this paper. It wasn't any other reason, and that's what you're explaining with your mathematical equations. Is that correct?
That's right.
Thank you.
Yes, that is correct.
Okay, cool.
Yes. Okay, so so that's basically what we need to look at there. So we can scroll down a little further. Okay, in the meantime, I can say that I'm going to look at what the temperature increase will be in the mantle, because when the mantle expands, it will put pressure on the crust. So basically, but then in the next diagram, as you can see, I only show the Earth's liquid core and the Earth's core. And now I have a current loop, which is a circle, on the outside of the Earth's liquid core. But I actually make it very thick. I don't even show how thick I make it. I made it so thick that it's about half the distance between the center of the Earth and the outer radius of the liquid core. But I didn't draw it as thick. I just wanted to show that I have a current loop there, or a current will form in the shape of a loop around the iron core. So, and I show the direction of the current. The current will be in a certain direction. Doesn't matter if it's in that direction or the reverse direction. It just will flow in a certain direction around the iron core. And I also assume that there's only one current loop. That really simplifies things. I would have assumed that that it caused a whole lot of current loops, and then I would have to add up the effect of all the current loops. But I just made it one current loop, which makes the calculation much easier to do. All right, so once I have the current loop, I calculate what the current is using Faraday's law. So we can scroll down a little bit more.
You do so well on those graphics, by the way. They're just perfect on how you explain things, because some of us, like myself, are not wired to understand math in any way, shape, or form. So I am very slowly following along, but steadily. So I appreciate your patience with me.
Oh, good. Thank you for, I like drawing diagrams. I think pictures say a lot more than words.
Yeah.
Because a picture, you can write a whole essay and then you represent it with a picture, and you can instantly see what you would take half an hour to read all the words. So that's why I really like explaining things with pictures. All right, so the equation is a standard equation. It's called Faraday's law. It's one of Maxwell's equations in the simplified form that Faraday came up with first, and he got it from measurement. He measured that a change in magnetic field, and it's got to change, causes a change in, causes a current to flow in another circuit nearby. Okay, so that current is called the induced current. And whenever you have a current, you have the equation is usually written in terms of an EMF, but I didn't go that far. I just wrote it in terms of the current and the resistance. And you know that if you have a current flowing in a circuit, there is a certain resistance associated with that circuit. There may even be resistors on it. So current and resistance always go together. So in this equation, I have current. I solve for the current. And the rate of change of flux, that's the d theta by dt. So d theta divided by dt, that's a derivative, which gives you the rate of change of flux. And basically, if the flux changes, then we're going to get a current. That's basically what the equation says. I know derivatives are a little bit more difficult to understand, but it means that something has to change in order for that function to have a positive value. If nothing changes, then d theta by dt will be 0. That's basically what it means. All right, so R is the resistance in the liquid core, because now we're going to assume the liquid core is like a circuit, okay, in which we're going to have a current flowing. So it will have a resistance associated with it. And the flux is the magnetic flux. Okay, I don't actually calculate the whole thing here, but I just put in the flux is basically the magnetic field times the area in the
that it penetrates.
Yeah, that's right. So I just use the area of the loop, which is, the area of a circle, which is pi r squared. And the circle, the radius of the circle is the radius of the liquid core. That's why I use R, and then LC. The LC means liquid core. And the area is pi r squared because it's a circle. Right, and then when you differentiate the function for B, what you get out is in front is the omega. That was in the cost function. It comes out, and now you can write it together with the C naught, and the C naught and the B was in front of the cos. And then when you differentiate, you get another omega multiplied with those two. That's
so we're looking at number 5 right now.
Yeah, sorry, we're looking at number 5. So number 5 follows from number 4. So what I did was I performed the operation of differentiating the flux, which is, I don't give all the details. I guess maybe I could have given more details here, but I didn't. I just that, and that's where the omega comes from. It comes from performing that operation given by d phi by dt. And then I say, notice, I say maximum current, and I leave out the cost function. When you differentiate the cost function, you get a sine function. But the maximum value of a cos or a sine function is 1. So basically, I just am saying, by saying the maximum current, I'm saying, okay, I'm going to, instead of writing sine or cos, I'm just going to say it's 1. And I leave out the cos and the sine from then on.
That's easy.
Okay.
All right.
Yeah. All right, then I end up with that equation 5 for the current, which is the area of the loop divided by the resistance times the C naught times B times the omega, the angular frequency, okay? And then I want to know what to do about the resistance. I need to calculate the resistance of the liquid core.
Why?
Is because I cannot calculate the current if I don't have a value for R. I know B, I know omega, I know C naught, I know the radius of the liquid core, and it's, I give it as, well, it's in the diagram as well, it's 3,500 kilometers. So I know RLC, I know C naught, I know B, and I know omega. Now I need to know what R is in order to calculate that current.
Okay.
So what I do is I looked up what measurements have been made about the core's resistance, and it's usually given not in terms of resistance directly, but in terms of resistivity or conductivity. Okay, so I looked up the measurement for conductivity. So I got that out of a paper that I found on the internet. I know I don't give references, I should have probably, but that's what I did. And the value then that I obtained is 1.5 times 10 to the 6 per ohm per meter. So from that, you can calculate the resistance. There is a standard equation for getting the resistance out of conductivity.
And that's equation 6,
and
your capital R.
That's equation.
Right?
Yeah.
Okay.
And that's right. And that uses the length of the resistor divided by the thickness given in terms of the cross-sectional area of the resistor. Then the resistor basically, I assume, is now that current loop that we have, that I drew in that diagram of the current loop in the liquid core. So the length of this resistor is the length of that current loop, which is a circle. So it's the circumference of the circle. So it's 2 pi times the radius of that loop. So that's RLC. And divided by the cross-sectional area of the loop, which there I write as d squared. Okay, and I assumed here it was a cross section. It was a square cross section. Okay, so that's the simplest one to work with. So I assume that, and I made it of half the size between the center of the Earth and the outer radius of the liquid core. That's why it's a half times RLC. Okay, so that's a half of 3,500 kilometers. So from that, we can scroll down some more. And
that's divided by sigma d squared. Now we're going to go ahead and go to number 7.
Yeah, it's a little, all right, yes.
Is that right?
All right, so then I plugged in for the resistance. And it's a little bit of algebra to get to that current value. And now notice that the sigma is there instead of the resistance. Okay, so I wrote the resistance in terms of sigma and RLC, and I calculated then what the new equation for the current is. Notice it's got RLC cubed in it because there was RLC squared in the denominator. Okay, there was because of the d squared. So now we obtain an equation with RLC cubed, and notice the C naught and the B and the omega are still there, which we had before. In equation 6, it's still there in equation 7. We just wrote R in terms of the conductivity, which is sigma. Okay, so now once we have the current, we can calculate the power generated, and the power generated is by a resistor usually is given off as heat. So that's why you know, standard heaters are basically big resistors. You know, if you have a big heater, electrical heater in your house, you basically have a big resistor that gives off a lot of heat and warms you up. So so this is what I calculate, is the heat given off by this circuit or this induced current loop inside the liquid core by calculating the power. And the standard equation for power is I squared R. So that's the current squared times the resistance. So then I use the equation for current, which is equation 7. I square it, and I multiply by the equation for resistance, which is equation 6. And again do the algebra, and I obtain equation 8. I just multiply all the symbols together. Notice there's now RLC to the power of 5. Because the I squared, when it's squared, will give me RLC to the power of 6, but the resistance will give me an RLC to the minus 1, so that's why I end up to the power of 5. All right, so now, once I have the power, I know the amount of heat transferred out of this current loop. Now I want to calculate what kind of a temperature increase it would cause, okay?
To the Earth's mantle.
To the Earth's mantle. Because, so the amount of heat will translate into a certain temperature increase. But in order to calculate the temperature increase, I have to know what is the thermal conductivity of the section where this current loop is. So how fast, basically, there's a certain amount of heat, which is energy per unit time, that's created by this current loop. And then I want to know, depending on how fast it can be conducted through this medium, what kind of temperature increase it will lead to. Okay, so again, I use a very simple mathematics. I assume a steady state. Okay, I don't want to go too much into that. A steady state means there, say if you have, yeah, maybe I should explain. So if you have a fireplace and you have a metal rod, and you put one end on the fireplace and you hold the other end, for a while the temperature across the rod will increase sharply. Okay, that's not the steady state. But you get to the point where you get to a steady state, that is the temperature at the fire and the temperature at the other end of the rod doesn't change anymore. So initially, you know, the rod is cold and it heats up very quickly. And then after a while, it reaches what's called a steady state, where the temperature doesn't change anymore. It just stays at a certain temperature, which is not the same as the fire. That's the steady state. So I assumed the steady state here to make the calculation easier. And it's just a linear calculation after that. And I again looked up what would be a good value for the thermal conductivity, which is the K constant there. And I found certain values, and I thought I would go with 44 watts per meter per Kelvin.
Okay, so you're looking at number 10 now.
Yeah, so number 9 then gives you, to calculate the steady state, the delta T means change in temperature. The T means temperature, the delta means change. Gotcha. So I'm going to calculate a change in temperature based on the P value, which is the power. And what goes into the equation as well is the distance. Okay, I did do something else. I assumed an area that the whole area, the surface area of the liquid core, the outside surface area, which is the area of a sphere, would be 4 pi RLC. The area and the thickness comes into it, but I didn't show the whole calculation. I just did the calculation and wrote down equation 9, and that's how it looks.
Okay, so for a second there, I thought you were referring to equation 10, but you were actually
No, I haven't got it.
explaining
Yeah.
number 9. Sorry, I
Yeah.
skipped ahead there. I was looking at the 44 from the explanation in 10 and
Yeah.
assumed that you had jumped ahead. Just kind of
Okay,
focusing
I
on the
went,
listener
sorry,
as
I
well
went
as
back
you.
a little.
Yeah,
Yeah,
well,
sorry,
you're really
I
smart. You're super smart, and I'm not to try to interrupt you. I think a lot of
No, no,
things
they're
are
cool.
assumed from your side, where some of us are not as quick as you, and so I'm just kind of working with you to help guide me understand exactly where you're at in the paper, as well as the listener. So I apologize if please don't be offended in any way.
Oh, Chris, you're actually helping me a lot, because to me,
Oh, okay.
I would just, you know, go through the whole thing very fast, because I did the calculation. So, you know, I need to see it from the viewpoint of someone else who hasn't done the calculation in order to explain it properly. So it helps a lot.
Oh, okay. Well,
right,
great.
so-
I appreciate that, because I'm really, from a layman's point of view, struggling at times, because you're extremely brilliant. So we're on number 9. You're explaining delta T being equal to the capital P was the power, or was that the? What was
the capital P is power.
That's
so
right.
it's the rate of energy transfer from the current loop, which I then want, from that I want to calculate the changing temperature, and the delta T is the changing temperature.
Thank you. Okay, that's where I was getting a little bit confused on. And then you divide that over 8 pi KRLC, and then that leads us into the next equation.
Yeah, so then what I do is I write out what the P is from equation 8, and that's the equation that you obtain, the sigma, the RLC to the power 4, the C naught squared, the B squared, the omega squared. And then I put in all the numbers, all the values that I have for every one of those. For the sigma, for the RLC, which you remember is 3,500 kilometers, the C naught, where I use the R, which is 7 times 10 to the 7 kilometers, and the B is 100 Tesla, and the omega is what I calculated right at the beginning, I think equation 2, where I used the T then was the period of 27 hours, and the K is that value given there between equation 9 and 10, well, 44 watts per meter per Kelvin. And then, so I get a temperature difference once I put in all those values, 690 Kelvin. Now, this is a temperature difference, so it doesn't matter whether it is in or Celsius, because there's a direct relationship for temperature difference between the two. So it doesn't matter. It's 690 Kelvin. But then I figure out what the Earth's temperature is at the core, which is 5,700 Kelvin. So this would mean a 12% temperature increase. And to me, a 12% temperature increase is quite a significant increase. And notice that I worked with a standard brown dwarf star, and I put it halfway between the sun and the Earth. So I didn't make anything, you know, I didn't take advantage of the numbers. I made it kind of a standard distance and a standard brown dwarf star. So to me, a 12% temperature increase is quite huge.
And
so that means.
Go ahead. Yes.
So that would mean that it would put a lot of pressure on the crust. Okay. So and obviously, if the two objects are in alignment, it might cause a spike in the temperature. So. And we're not sure exactly how long it will take for the mantle to react for the spike in temperature. It might actually take a few days. So, yeah, but that's basically the result from this paper. I just wanted to show if we could get a reasonable result. I mean, if I got a temperature increase of 7 Kelvin, I would say, okay, that's pretty tiny, or 2 Kelvin. But I got a significant temperature increase of 690 Kelvin. I think that's increasing temperature.
And what you're saying, just for the listener as well, is that you had mentioned in the conclusion that this was a significant increase, which would cause the mantle to expand. and thus
Yes.
place the crust under pressure, which will in turn lead to earthquakes and increased volcanic activity.
That's right.
Wow.
That's what it leads to, you know. I mean, I've been talking about this for a while, saying that having a brown dwarf star in the solar system will heat up the center of the Earth and cause volcanic eruptions and earthquakes. And I've also talked about the fact that every single planet in the solar system has warmed up, which is relevant as well, because obviously dwarf stars have affected all the planets in the solar system. And I just wanted to put some numbers to it to actually see what kind of effect we would get. And indeed, we get a significant effect from having just one single brown dwarf star in the solar system. And notice, we don't just have one, we have a couple. We have a few.
Well, that brings an interesting transition point. I believe today, Scott noticed that every single video from Dutch Synths had been
Yes.
demonetized for 5 years, that this young man has put out material, that YouTube demonetized every single one of his videos. And we know Dutch Synths well because he is a amateur volcano and earthquake predictor and does a pretty dang good job and is actively
Yes.
trolled by agencies like USGS, etc. And they have no problem letting him know, as well as his subscribers, that they are trolling him actively. I find it very unusually timed that happened. I just wanted to mention it.
Yes, indeed. I think it's unusual as well. But don't forget that it seems that the powers that be are desperate to hide the fact that we have extra brown dwarf stars in the solar system. They seem desperate to hide the fact that these brown dwarf stars are affecting our planet and that they are causing earthquakes. I think we've caught them just removing earthquakes, not show, you know, from the maps, and downgrading them. And a few years ago, I think they actually rated the magnitudes differently so that earthquakes look weaker. They obviously knew what was going to happen, and that is happening now. And that's why I think they did that. Basically, they are trying to hide the fact that there's something going on in the solar system. And we are doing the opposite. We are trying to tell people the truth. There's certainly something going on in the solar system, and it's significant. There's something going on with our planet. The earthquakes are getting worse. There are more of them happening. And I think that's why we are on opposite sides of this information war.
That's exactly what it is. It's an information and technology war, because they're able to skew their technology, you know, with the animations that we look at for the magnetosphere. Matter of fact, I've been looking at them for the last couple of days, and they just look completely normal, but the actual numbers, they just don't jive. Because when you're taking a look at some other data and you're taking a look at their computer animated models, they just don't match. They just don't match at all. Especially when, you know, I'm looking at the radiation enveloped around the Earth and the satellite belt, where we see these, you know, large deposits of radiation just whipping around the Earth. Okay, well, where are they coming from? Where are they coming from? But the other data says it's not happening. But yet your one model shows that it is happening.
Yeah.
And now all of a sudden we're getting days and days of delay of this data. Usually it is up there within 24 hours. Now we seem to be lagging about 72 hours. So I think during that period of 72 hours is where they get their little paintbrushes and the little paint by numbers and the magic markers and colored pencils, and they start covering everything up.
That's right.
They've been known to do that. It's been proven. They've been outed on that years ago. But now, when things are getting very critical, you know, they're going to make every single attempt. Now, there was something I wanted to ask you, Doctor. Over the course of the last couple of days, in the southern hemisphere, we've had some very, very deep earthquakes. One of them registered over 250 kilometers deep, and then there was another one in the southern hemisphere that registered over 400 kilometers deep, and they weren't too far apart. Now, at the distance of about 250 kilometers to 400 kilometers, those earthquakes are occurring where? In the mantle? Is that how deep they are?
It depends, because the crust is very thin in the ocean, so it could be as deep, in the mantle if they are in the ocean. But the crust is thicker in the land masses, so it could be in the crust still. If it's under a under a land mass, under a continent. So it depends whether it's over the ocean or but these deep earthquakes are because there are fault lines that go down that deep, I suppose. I mean, don't forget the Earth is, radius of the Earth is 6,370 kilometers. So 250, it's not down that far, but it is still deep, because we're supposed to have, most of the earthquakes are supposed to be closer to the surface. That's where most of the fault lines are supposed to be.
Yeah, so when we see these deep earthquakes, because I follow Dutch since religiously, and just to reiterate what Chris stated, the situation that happened with him is just absolutely terrible. His earthquake forecasting is just absolutely impeccable. And yes, there are a few people that are higher up in the USGS, and they actually troll him. They actually taunt him, and they pretty much make fun of his earthquake forecasting. But I watch every single report that he puts out, and very rarely is he wrong. And I'm talking, he is pretty much up there in the high 90% percentile as far as, getting these earthquakes as close as possible in a geographical area. I mean, naturally, we're talking about, Mother Nature here. No one's going to actually pinpoint an epicenter, but whenever you're getting them within 100 miles or a few hundred miles, well, that's pretty good. That's better than what they're doing.
Yeah, well, I haven't watched him for a while, but I think his logic is sound, because as he sees an earthquake happening somewhere, he deduces that it's going to affect the next fault line, or it's going to travel along the next fault line and impact a certain land mass adjacent to that. I think his logic is sound in the way he does that. So I really think he's doing a really good job. Much better than USGS, which is probably why they troll him.
Yeah, there's
jealousy.
There's no doubt about that. And I think you're right. I think there is some jealousy. I think he could probably walk into the USGS and take over the whole operation.
Yeah.
And make
you do a better job.
Yeah, we know that would never happen. So basically, do you think that we have a dual combination effect right now on the Earth? For instance, the high impact of the particles from these coronal holes, and the combination of the presence of the brown dwarf, that these two factors, they have to be at the top of the list, like number 1 and 2, as far as what is creating the earthquake situation on this globe.
Yeah, well, you see, what we have is we have brown dwarf stars around the sun. I think these brown dwarf stars are not as strong magnetically as another brown dwarf star that seems to be, or have been up to now, in the outside of Earth's orbit. And the magnetopause reversals happen when the Earth is in alignment with this very strong magnetic brown dwarf star and the sun. So I calculated where it was in October of 2016, and I calculated, using the magnetopause reversals of 2016, that it was somewhere between Jupiter and Saturn. I got 6.9 AU as its distance from the sun. And now I have just calculated it again, because there was that, I don't even call a magnetopause reversal, I call it a magnetosphere collapse that happened on March 14th. And I've calculated that again, and I've calculated that it's much closer now than it was then. I know that Chris hasn't put out the video yet, so maybe we should leave it for another interview. What do you think, Scott?
Yeah, we'll go ahead and we'll work on that, possibly maybe tomorrow or the next day. What I wanted to do is I wanted to get your opinion on this photograph that came in from one of my subscribers a few days ago.
Yes.
And she actually caught this on the International Space Station footage before they cut the feed. And she, naturally, you know.
Yeah,
always a technical problem.
The feed.
You know, they have so many technical problems up there in that International Space Station, you know, so many glitches. I would actually be terrified if I had to survive all of that distance above the Earth, floating around in this tin can with all of these glitches and technical difficulties. I would beg for them to please come get me and put me back on the Earth. So I don't buy, you know, I don't buy all of these technical glitches. All of a sudden, when something appears in the sky, in space, right in front of the camera, I mean, they even caught one of the astronauts actually putting his hand over the camera to block a UFO that was zipping by in a V-shaped pattern, which we know that wouldn't be a space rock, meteor, or asteroid. That would have to be something with intelligence. But whenever my subscriber sent this photograph into me, I was pretty thrown back by what I saw. And I examined the photograph for hours and hours and hours and changed multiple filters. And I used, oh my goodness, I think I used over 15 different photographic techniques to bring out these two objects.
Yes.
And you know that we've seen this striped object many, many times. I've taken photographs from it from webcams in Australia. I have a telescopic photograph of it from one of my subscribers from last year that was able to, you know, capture this by accident, really.
Yeah.
You know, I mean, the gentleman thought, you know, well, first he didn't even know what he was looking at. And then he sent me the photograph. And then it was many, many months later that we discovered this large striped object was now appearing in, you know, other photographs that were coming from the International Space Station. And as soon as it's seen, they cut the feed.
Yeah.
But what do you actually think about this object?
All right, the striped object. It looks like a planet. It seems to be reflecting a little bit of light, so it's probably being illuminated by a star. So if it's being illuminated by the sun, we would have to place it where the sun is or below the sun. So that would make it absolutely huge. As you can see, I mean, if that was the standard size of the sun, that light source, and I'm going to say it's not the sun, but if it was the sun, this object would be larger than the sun, or maybe the same size as the sun. And I mean, planets are not usually the same size as stars.
I mean,
so it could be that
the light source that we're looking at. I mean, I've seen many, many photographs over the years of the sun, you know, in space. This object doesn't look anything like what I've seen many, many years ago. This just looks completely artificial. It looks like a bright halogen flashlight.
Yeah, I think you're right there, Scott. Notice the little object a little below the light source. Okay, it's bright, so it looks like it's emitting light. Okay, and you can see it shaped pretty well. I mean, it's not quite as bright as the sun, but it's nearly as bright as the light source. So I would say it's a star. Plus, if it was being illuminated by a star, probably not. We'd probably see it as a crescent, like we see the planet, the large planet with the stripes. So that object to me looks like a star. It's very bright, but it's in focus. Look at it. We can see its outline clearly. It's in focus. Whilst the object that we're supposed to think is the sun is completely out of focus. And there's no reason why it shouldn't be out of focus. I mean, if the little object below it is in focus, why shouldn't the sun be in focus? If it was the sun, there's absolutely no reason why it should be, but yet it's not. So what I think it is, it's and look at that. It looks even worse there.
Yeah, this photograph has the full color. This was
okay.
This photograph here is the actual original.
Okay.
Okay, so
yeah, I mean, it looks even worse.
Yeah, I took about 70, I think it was 78, different screenshots of this object and this photograph, and trying to change the coloring a little bit so we can see the object more clearly, and putting it into that that old-fashioned sepia look gave it some pretty good detail. But this original is pretty. I mean, if you look at it, it almost reminds me of Jupiter, because it has.
It does.
This large circle in it. But we know that this is not Jupiter in any way, shape, or form.
No.
And it's still.
There's no way. Yeah.
Still an amazing photograph.
So it is. I mean, so that object, because of the stripes, would have to be either a gas giant like Jupiter or a brown dwarf. And I mean, the brown dwarf is the substellar objects that are between gas giant planets and small stars. So, I mean, it looks so huge. I would say it's probably a brown dwarf. So there's probably, and I don't mean a brown dwarf star. I mean, I differentiate between the two. This would be a planet-like object, like a gas giant, but larger. And it could be what we call brown dwarfs.
Now, I just wanted to point something out, ladies and gentlemen. If you take a look at the sky, if you follow my cursor, just take a look at all of the cloud cover. And all of the cloud cover in association with what is right there in the sky, in space, right by the sun. So therefore, if they do not chemtrail and hide these objects, you would be able to see these objects at some point in time. That is why when you go outside and you take a look around, look away from the sun, you'll see clear skies. And then when you look near the sun, then you will see all of the chemtrailing back and forth, the tic-tac-toe signs, the whatever design pattern they want to make. They're going to block that sun out, because this object is going to be staring you right in the face. And the size of this object, I mean, it's very hard to understand the depth perception, the distance perception of this object, because even the sun, whatever this bright object is, we don't know. That doesn't even look like the sun. It just, I'm sorry, it just doesn't look like the sun.
Yeah. I don't think it is the sun, Scott.
No, it
I
looks
think
like
it's,
a big space flashlight.
Yeah, and what they do is the devices produce a light that's small, so they put a lens in front of it that causes the light rays to diverge, and then it makes the light source look larger, but it also causes this out of focus effect that we see here, and it looks diffuse around the object. That's all because of the diverging rays of light coming off from the lens.
I wanted to mention to you yesterday.
Yeah.
I was out and about running a few errands early in the afternoon. Oh, maybe 12 o'clock noon. And just as I was ready to walk into this store, I noticed, I wasn't the only one, other people in the parking lot getting out of their vehicles noticed that the sky was crystal clear. There wasn't a cloud in the sky. The sun was shining, or what we think is the sun. And then all of a sudden, it was like everything got very dim for about 3 or 4 seconds. but it was very, very noticeable because everyone else that was walking through the parking lot stopped, and they turned around and they looked up. And I did the same thing. I mean, I saw it with my own eyes.
Yeah.
And there was no cloud cover, there was no chemtrailing, but yet there was this flash and everything went dim. It was like they turned the light down and then back up. And I don't know how that is even possible for something like that to occur without something passing in front of the sun for a minute.
Yeah, I mean, a couple of things could have happened there. The actual sun could have been eclipsed, but if it was only for 3 to
5 seconds at the most.
Yeah, I'm not sure. It could be that the device they were using malfunctioned for a few seconds.
Oh, there we go. More glitches by NASA.
Yeah, the thing is, if you rely on devices, they usually malfunction now and then. So that could be it. It could have been an eclipse, I suppose. It could have been that an object passed in front of the real sun. The Earth's atmosphere is still being illuminated by the sun. I mean, they have a couple of simulators. They even have these ones that operate at cloud altitude now that look very round, but not actually round. But they have all kinds of simulators in the atmosphere. And I think actually they position them most of the time specifically to hide the extra stars and planets around the sun. So that's what they mostly trying to do, is hide these objects. So I think they must have quite a few of them. And
yeah, I would say because of the different shapes that I see, and these are in my own photographs and my own observations. Yeah. And, you know, 1 minute it's perfectly round. The next minute it's shaped like a horizontal diamond. Yeah. Then the next minute it's shaped like a vertical diamond. I've even seen it in a hexagon shape. There was one gentleman that took a photograph of it, and it was in the shape of a Jewish star, the Star of David.
Oh my.
And he took that photograph from the mountains. I don't know if it was either in California or I forget, it was out west somewhere. And he sent me the photograph late summer. And I was really just thrown back by what I saw, because there's no way that the sun can form a 6-pointed star shape.
You're right, yeah, no way.
You know, what I wanted to ask you also, I've been getting a lot of people that have been sending photographs in the last couple of days of the moon. And I was out the other day with my little telescope, and, you know, I was taking some views of the moon, and the moon was out at 4 o'clock in the afternoon, and it looked like you could just reach out and touch it. And then based on the diameter of the moon, based on the distance from the Earth to the moon, you know, we're talking about close to 240,000 miles. The moon is what, like 2,600 miles in diameter? Something like that?
I don't know offhand, sorry.
I think
yeah,
something like that. So, I mean, that would make this object either closer to Earth closer to the moon. I mean, it really puzzled me for a minute, because it looked like you could just reach out and touch it at 4 o'clock in the afternoon. I mean, you could literally see the surface of the moon, and it was a little disturbing to see that at 4 p.m. and the sky was crystal clear.
Yeah, you see, Scott, it's very easy to turn a sun simulation device into a moon simulation device. You simply turn down the light, and you get the holographic projector that operates with it to project the surface of the moon instead of projecting the surface of the sun. So the holographic projectors operate with these objects because, first of all, with the sun, they don't want anybody with a solar telescope to point the telescope at the sun and see anything but what they expect to see, which is what the surface of the sun is supposed to look like through a solar telescope. And they do the same thing with the moon. They simply project the surface of the moon, and they don't always get it right. But that's why it looks so much closer, because the moon simulator is a lot closer, and the holographic projection is a lot closer. It's not the actual moon. And again, they do the same thing because often in the night sky, there are objects to be hidden as well. So they put the moon in the right place in order to hide these objects, if it works, you know.
Yeah, so once again, you know, we have so many unanswered questions, you know. I just wish that, once again, I'll say it again, I wish they would just step up to the plate and say, listen, ladies and gentlemen, this is what we have going on. There's not much we can do about it, you know. I mean, let's just try to band together and make it through this. But, you know, they just want to keep continuing with, you know, hiding the objects. And, you know, I remember, you know, speaking with Gil Broussard on a phone call, and, you know, he just came right out and said it. He said, listen, Scott, the day is going to come when the devices and the technology that they're using to mask these objects, it's not going to work anymore because the objects will be too close to the Earth. They were once relying on the distance, which made it easier. But as the objects move closer, your technology is not going to work. So then what's going to happen is people around the world are literally going to step outside and look up and possibly see something that they've never seen before.
Yeah, that's right. It's also because the brown dwarf stars that have come in, when they first come in, you don't see them. They don't emit much light. But within sometimes a couple of months or a couple of years, they start emitting light. They become visible. They start illuminating the Earth's atmosphere. That's why we see these red clouds and so on. So as they become more, they emit more and more visible light. They become more and more difficult to hide. Okay, so we are seeing strange effects, right? A red atmosphere, red clouds, pink clouds, orange clouds. Those are not normal. And they are hoping that people don't notice these things. But the fact is, it's happening more and more. It's becoming more and more visible, the strange things that are going on in the solar system.
Yeah, strange. Using the word strange is a super understatement, because I'll tell you what, I mean, every single day is, I don't even know how to explain it anymore. You know, it's whenever I wake up at 3 o'clock in the morning and I get to, you know, analyzing all of this, answering emails, looking at photographs that people are sending in, and taking a look at, you know, some of the data that's out there that's not skewed or disguised. And then you know, you come across a photograph like this that was just taken a few days ago, just a few days ago. And more and
there
more,
you are.
Yeah, and more and more
There's a
people.
star.
Yeah, it's incredible, because more and more people are actually waking up. And then now, you know, we have this big shakeup within YouTube, and they're literally, you know, trying to get rid of, you know, YouTube channels that are reporting on controversial subjects, whether it be politics or, you know, possibly subjects like this. Now, I know that they have messed around with my YouTube channel, my subscribers, their notifications and things of that nature, but we're still here. And as I mentioned the other day, that is one reason why I opened up the new internet radio station, which is the X Factor Radio. And we're going to be doing radio shows uncensored with no problem, and they will be uploaded to both of my YouTube channels as long as they stay up there. But everyone will have the ability to come to the radio station, and you can listen to the interviews, the commentary, and the reports 3 or 4 times a day. And it also gives us the opportunity to show some pictures. You can create a slideshow of photographs to put up there, actually on the front page of the radio station, X Factor Radio, because you know what? That's what we're talking about here. We're talking about the X Factor, and the X Factor, as I'm looking at this photograph, is this big striped object. Let's just put a big X on it.
Right.
You know, because it is the X Factor.
Sorry, Scott. I would put another X on that little star below the light source. The stars around the sun. You see that?
Yeah, and it's
That's
not a
one
lens
of those
flare.
stars.
You know, it's not a lens flare of any kind, because I put, like I said, I put this photograph I worked with it for, oh my, hours and hours. I worked with this photograph, and you know, I was putting it through multiple filters to try and bring out these objects.
Yeah.
Now, you can take a look. We'll just take a look at the little object first.
Yeah, you see, it cannot be a lens flare. How can a lens flare be more in focus or have such a defined outline than the brightest object in the image, which is that out of focus light source? It's impossible. If it was a lens flare of that light source, it would have the same shape. It would have that irregular, you know, rays coming out of the kind of shape that it has, because it's totally out of focus. It doesn't have that shape at all. So it's not, cannot be a lens flare of that all.
I mean, it looks like a planetoid of some kind to me.
Yeah.
You know, I stared and stared and stared at this photograph. I was up.
Yeah, you see, it's not as bright as the light source because most of these stars are not emitting as much light as the sun. I think that's what it is. But it's bright enough for me to think that it is a star. It's emitting its own light.
You know, and then just taking a look at this sun object, you know, and all this is an inverted photograph. But
yes,
you know,
so the black is actually the bright.
Yeah, I mean, just looking at this was, you know, I've taken many photographs of the sun using filters. I've inverted the photographs. Never have I seen anything looking quite as strange as what we're looking at here today on this ISS photograph. And then, you know, moving back to the big X factor planetoid massive object here, you know.
It's
now, naturally, the troll babies were out there yelling and screaming and jumping up and down. You know, it's a lens flare. It's a lens flare. Well, I'll tell you what.
It's a lens flare of what?
Yeah. Yeah, tell your mommy.
It cannot be a lens flare.
Yeah, tell your mommy to buy you some glasses because, you know, I don't. You know, that's just an incredible photograph. It has to be one of the best photographs that we've had so far this year in 2017.
Yes.
And it's still absolutely amazing. And it makes me want to know exactly where this big bad boy is located. And I want to see, you know, an actual high definition telescopic photograph taken by NASA and all of their technology. And I want them to show it to the world. But we know that's not going to happen.
No, I don't think so. Yeah, it would be nice to actually be able to see all these things. If NASA was actually doing what, you know, they were supposed to do, which is actually show us the truth. But I guess they will never do that.
You know what I was actually thinking when I was looking at this photograph? I was thinking about the people in the space station, the astronauts. You know damn well that they're seeing these objects. And I mean, could you only imagine the fear that would set in if you were in this space station and you've never, in your career as an astronaut, you've never seen anything like this, but now you're looking out of one of the little porthole windows of this tin can in outer space with all of these technical glitches, and that is your view.
Yeah.
I would be screaming on the microphone to get me the hell out of space right now.
No, they're obviously not that afraid. They obviously don't think the objects are going to come close to them. And they have gag orders, I suppose, so they will never, you know, speak about it. But they obviously must know what's going on because they see it. I mean, if they didn't see it, we wouldn't have this photograph.
Exactly. Now I darkened this photograph because I wanted to get a closer look at the sun, whatever the hell it is. And it just didn't look normal. And I was trying to see if I saw anything around the sun, like a mechanism of any kind. But then I started zooming in on that smaller object, And this smaller object, I mean, you can literally see a surface of some kind on it.
Yeah, you see, if it's a brown dwarf star, it can have, you know, that kind of gaseous cloud that sometimes envelops the star. So it could be that. I don't know. I'm not sure what it is. These brown dwarf stars have strange shapes sometimes.
Yeah, there's no doubt that was definitely one of the craziest looking photographs that I've ever seen.
Yeah.
You know, and I've been doing this a long time, trying to search for these answers. This is just one more photograph that a little bit of a different technique was used as far as the filter goes. It actually turned these large panels on the space station from gold to pink. But yeah, but it actually brought.
If you look at the atmosphere, there's a bit of a pink tinge on the atmosphere as well.
Yeah, I did notice.
Look at that. Did you notice that? So that to me tells me that, I mean, the whole scene is being illuminated by magenta light, and this is a lot of photographs have been taken of clouds on Earth that are magenta colored. So what we could have is that part of the atmosphere being illuminated by a magenta emitting star. And I mean, I'm looking at that object. It looks very bright. It looks like a star, but it could be that it's a planet that's being illuminated by a star. But I don't see what it could be then, because it looks so strange. Or it could be another one of their devices. You know, it could be two devices there.
You mean the smaller object?
Yeah.
Yeah, it could be. Lord only knows what's out there. I wish I would have been able to actually see this on the actual video, you know. But we'll never see this again.
Can't.
You know, you can guarantee that. We'll never see it again.
Yeah, the most interesting part about that image is that everything looks pink. So everything's being illuminated by pink light. And that means that there's a star emitting pink light somewhere. The reason we can, I mean, look at the atmosphere. It looks pink as well. The clouds don't look white. They look pink. And there it looks blue.
Yeah, this was just another different filter, and I was just trying to bring out the definition in this object, and the blue actually, whatever I forget what the
I see. Were you using filters?
Yes, just these. It's actually a website that I use, and
okay.
a pretty sophisticated website, and there are over 50 different photography techniques that you can use to modify a photograph. You know, using gamma, exposure, the inversion. Oh my goodness, there's like 50 different options, and you're able to make the proper adjustments, and then it brings the photograph out to you. You can zoom in, and you can crop the images. You can do a lot with it, and it works very, very well because, you know, a lot of these objects they turn up the intensity of the light, and when you do that, these objects disappear. So whenever you lower the brightness and you lower the exposure, then you can see these objects hidden in the darkness.
I see. Okay. Now, I actually thought it was pink light and blue light, but I see you just using filters.
And this one here, I mean, this really brought out.
That's, yeah, that looks amazing. You can see the different colors in the object, the stripes. And it's huge. It's absolutely huge. And you don't see the whole object there. For it to be illuminated by the sun, it would have to be under the sun to be illuminated like that. Or maybe slightly, I mean, and that would make it about the same size as the sun or larger. And don't forget, Jupiter is 1/10 the size of the sun. So this object, if it was the same size of the sun, would be 10 times the size of Jupiter.
My God.
That is huge.
You know, and it just burns me up that people say, oh, there's nothing going on. There's nothing in the sky.
Yeah.
You're fear-mongering. Okay, well, explain this damn photograph to me then. Explain it. step up to the plate and explain what we're seeing, because it sure as hell isn't a light anomaly or a lens flare, because I have other photographs of this object.
Mm-hmm.
And it is identical to what we're looking at.
Yes.
Yeah, it just gets me.
So it's obviously,
yeah,
it's obviously in the solar system. It's in the inner solar system because we see it close to the sun. So it obviously orbits. It probably belongs, is a planet of one of the stars we have in the inner solar system. That's why it's always around.
Yeah, I'm actually trying to find the photograph that that I was referring to. Well, I'll tell you what. Here we go. And here is a photograph that was I did a story on that I captured. I captured these photographs, and you've seen these before. I captured this photograph on a camera in Bondi Beach, Australia, and there it is.
Wow. Well, it looks smaller there compared with the sun. There it looks.
Now this is many months ago. This is probably 3 months ago. 3 months ago, this photograph was captured, and there's some light enhancements that were done on this to bring out this object. But when you look at it, the patterns of the stripes on the object are the same.
Definitely.
So
Definitely.
you know, I mean, there's only so much that you could say in resistance to what you're seeing.
That's right.
I mean, okay. So, you know, now we have this big object that the space station was able to catch a photograph of in early April of 2017. This object was captured, I believe, back in January, as I was looking at these cameras in Bondi Beach, Australia. Okay, so somebody please, you know, if you have a better explanation than, you know, than I do, then I would love to hear it. Here is the object that I was referring to. I'm going to go ahead and screen share this real quick so everybody can see the difference in what I am talking about. Now, this was captured by a telescope.
Yeah, I can see it's a telescopic image.
Yep. So there we go. There are the stripes.
That's amazing.
Yeah, I mean, I don't know what more.
Now that is good.
Yeah, I don't know what more evidence that people want other than to show you what has actually been captured on film, you know, camera, digital, whatever. The bottom line is this massive monster of an object is floating around in our inner solar system. There is absolutely no doubt. None. Zero.
That's right.
I mean, look, if you look at the object, I was looking at this mark right here, and I thought maybe this mark was something on the internal mirror of the telescope. But as I looked at it closer, it actually looks like something impacted here.
Yeah. In fact, the object is full of impact marks. If you look at it, some of them are a bit faded because it's obviously a gaseous planet. So when something impacts it, you can see a couple of faded craters. Something impacts it, it goes right into it and leaves a kind of a scar, and then it sort of fills in. You can see the large black one is probably a recent one. We can see right into the object one. You can see it's dark inside. We can see it obviously got impacted by something, and it left a hole. So it's quite recent. But we see these other ones that are faded and sort of filled in, and it just looks like an indentation. It's a little darker. So this obviously has been heavily impacted by other objects.
Oh, there's no doubt about it. When I first got this photograph and I looked at it, I said, "Oh, wow, that's a cool picture of Jupiter."
Yeah.
And I'm like, okay, well, wait a minute, that ain't Jupiter.
That's right.
This photograph was accidentally captured. You You know, and then it's just an amazing photograph. It's a one of a kind.
Yes.
And I was looking at this black smudge up here. Once again, I thought it might have been dirt or something, a particle on the mirror in the telescope.
Yeah.
But then I started to think, well, you know, that could have been some type of a volcanic explosion, some type of a plume of, you know, a discharge of some kind, because it doesn't look flat to the surface.
No, it doesn't.
It actually looks like it is, you know, it is coming out of the surface and rising up into the, whatever you want to call it, the little atmosphere.
Yes.
But it is an amazing photograph, and it's, again, it's a one of a kind. And it's kind of unfortunate that the gentleman that took the photograph, I've actually lost touch with, because he's over in Europe, and they've done something to my YouTube channel. So a lot of the European subscribers, I had over 25,000 of them, and I was communicating with them all the time. People from Switzerland and Germany and Belgium, you know, and all of these countries. And now I very rarely hear from them.
Yeah, that's a pity.
Yeah, it is, because they were coming up with some very, very credible and incredible photographs and information.
Yeah.
It's very, very sad.
It is indeed. Well, that's probably why the powers in that be blocked that. They didn't like that flow of information.
Yeah, because I know I probably opened up some eyeballs whenever this photograph and this video came out about this big monster. Because in order to capture that with a pretty sizable, you know, ground-based telescope, this is just one hell of a photograph.
It is. It's amazing.
But I guess sooner or later we will definitely find out what's going on in our solar system for a fact. But what I'd like to do, Doctor, I know you have some calculations that you've made on the positioning of this brown dwarf star, and based on your time and your busy schedule, maybe we could get together either tomorrow or Wednesday or whenever your schedule is clear.
Yes, sure.
Maybe you could bring forth, you know, some of your calculations, and maybe we could get a bead on where exactly this object is, and maybe we can get, you know, 50,000 sets of eyes out there, and maybe somebody will come up with an absolutely incredible photograph that will stun the world. I actually think we already have photographs that would stun the entire world population, but I don't think the whole entire world population is going to see my YouTube channel. That much is for sure.
Well, maybe the more of them will listen to your radio programs.
I hope so. I hope so. I've been letting everybody know that the link for the Blog Talk Radio, X Factor Radio, the link is in the description box. You can go ahead and click on that link, go directly to the station, and click on the follow link and set your notifications up, because we're going to start with our programming probably in about 2 or 3 days. I'm just working some things out and learning how to use the dashboard, and we will have call-ins. There'll be a call-in number for the viewers, and we are going to get down to the point where we're going to have the viewers, the subscribers, the ordinary people on this globe getting on the telephone, getting on the radio show, and I want to hear their voices. I want to hear their words. I want to hear what they have to say, each and every person's observations. I want to hear your story, and that's exactly what we're going to do. We're also going to have other guests on the show that have done very in-depth investigations pertaining to Planet X. So, Doctor, any last words before we end our program?
No, I'd like to thank you, Scott, for letting me go through my paper and explaining my calculations. That was fun.
You know, no disrespect, but your calculations, that mathematics, oh, that brought back nightmares from high school. Oh my God.
So sorry.
Oh my Lord. I had to take 2 Tylenol because all I could hear, I went to Catholic school, and all I could hear was the sister smacking me with that little wooden ruler because I just could not comprehend that type of mathematics. And thank God that, you know, we found you and you found us, and it's been really, really interesting listening to you and having someone with your intelligence level to help all of us explain this, at least in terms that we could understand. And it was absolutely, just absolutely amazing looking at your mathematics. I don't know how that sounded just now, but your mathematics are very beautiful.
Thank you, Scott. That's lovely.
If you just want to hang tight with me for a second,
okay.
Go ahead and let everybody know. Listen, ladies and gentlemen, once again, you know, we're trying to come back and deliver to you some groundbreaking information in this research and in our investigations. I hope it opens up your eyes. I hope that it is your awakening, and I hope that you do understand that there is something or some things in our inner solar system that may possibly be a major threat to our planet. I don't think that it's going to be a threat to our existence, but in the future, it is definitely going to play a role in what happens on this planet. And it already is. As I've mentioned before, time and time again, all of the signs are there. And this is not going to be an event that lasts for just one day. What you're looking at now is the precursor to what will come. And preparation is something that everyone should do, even if you just do a small amount of preparation. I mention all the time about getting your bug out bin together. Buy one of those large plastic bins. Put your canned foods, your non-perishable foods, bottled water, an emergency medical kit, medications that you may take, an extra change of clothes, blankets, whatever you feel that you need. Have that bug out bin ready to go. If you are evacuated for any reason whatsoever, at least you'll have some of your things that will be a big help. I'd like to thank all of you very, very much for contributing to the Planet X News and the Nibiru channel. We have a lot of people over the course of the last several days that have made very beautiful donations to the Planet X News channel. Because of what YouTube is doing, it's definitely helped keeping the lights on for this channel. And hopefully YouTube gets everything straightened out and we can go back to investigating what's happening and spreading the word and trying to awaken each and every one of us. So ladies and gentlemen, this is Scott and our doctor of physics from Planet X News. Thank you very much for watching. Hello everybody, welcome back to Planet X News. This is Scott from the Nibiru channel. Excuse me. I have Chris Potter and our physicist here, and we're going to be talking about why the Earth's mantle is heating up, the increased internal temperature. So, Doctor, how are you this afternoon?
I'm very well, thank you, Scott. And how are you?
I'm doing pretty good. Christopher, how about yourself?
I'm doing great. How are you?
I'm not doing too bad. The temperatures are 81 degrees here. The chemtrails are out. They're blocking out the sun. Just absolutely incredible what they do. As soon as the blue sky appears, the chemtrail planes are out there like little spaceships, mucking up the sky. Makes you wonder. But anyways, ladies and gentlemen, we're going to be getting into an article, and the article that the doctor wrote is concerning the internal temperature increase in the Earth's mantle, and it is due to the presence of a brown dwarf star in the solar system. And this was dated just a few days ago, and she's been doing some absolutely incredible work. And over the course of the next several days, we're going to be having some groundbreaking information. We're still actually working on it at the moment, and we could have it back to all of you as early as tomorrow, possibly Wednesday. So definitely stay tuned. So, Doctor, you want to go into this very, very impressive report that you've established here. I was reading over it earlier, and this will definitely be something that you will have to explain. So I will give you the floor.
Okay, thank you, Scott. Well, it's actually a very simple model. I use very simple mathematics. I know it looks complicated to you, but I'm just using pencil and paper methods. In other words, I didn't use any computer modeling to do this. I just I make a few assumptions, which I think maybe I should talk about.
Why are assumptions important?
Well, you always start out a model by, you have to make assumptions because the model has to be simplified. It's not a real world model. I mean, the model models the real world, but it's never the real world because there are too many variables in the real world. So as far as I'm concerned, I like to start out by simplifying things as much as possible. I know that nowadays physicists like to make things a bit more complicated than I think they should be. And I mean, it's come to the point that, you know, people think that physics is good because it's very complicated. But I think you only need to complicate it more if the first result is not good enough. So you should make it as simple as possible, at least at the first attempt. So this to me is a simple model that I just wanted to see if I could get, if I put a brown dwarf star with a kind of a standard size and a standard magnetic field at a distance which is like halfway between the sun and the Earth, which is a kind of a standard for me distance. So that's the first assumption, that first of all there are brown dwarf stars in the solar system. Well, to me it's not that much of an assumption, but you know, I know that they are there and that they are in the inner solar system. So basically I assumed a distance that is reasonable to me. Okay, so you always try to make an intelligent assumptions. So I start out by explaining that brown dwarf stars come from white dwarf stars. They just cool down white dwarf stars. So they don't emit much visible light, which means they will have a surface temperature of about 1,000 Kelvin or less. So it takes a while for a white dwarf star to cool down to a brown dwarf star. But that's not what's important here. What's important is that they have very high magnetic fields, because when white dwarf stars form, they collapse into a much smaller size. So they can go from being the size of the sun to being the size of the Earth. At least that's theoretically what's been decided. I'm not completely sure about that, but I'm using the standard astrophysical theory on that. So I'm taking a standard white dwarf that has cooled down to become a brown dwarf. So it's about the same size as a white dwarf, which is about the same size as the Earth if the star initially was about the same size as the sun. Okay, so those are my initial assumptions. Okay, if you can scroll down a bit further, we can get into what I say after
You
that.
can scroll down a little further.
No, I think
Yeah,
that's
please, Scott.
Oh, okay. Well, I'm going to interrupt a little bit.
Yeah.
When you mention its magnetic field, and you mentioned the size, for example, the size of an Earth, is the mass increase on a star that goes from a, you know, white dwarf to a brown dwarf? Actually, is that a given, or go ahead?
No, it doesn't actually lose much mass, but what happens is it becomes extremely dense, okay? Because it basically, well, the theory is that gravitational collapse, once the nuclear reactions have stopped, it collapses due to gravitational attraction towards the center, so it becomes very dense. Okay, my own observations have led to me to believe that what happens might be different from that, but I'm just using the standard theory here. So basically the gravitational attraction causes it to collapse into a much smaller, much denser object than it was, especially in the red giant phase where the outer layers are very diffuse and it's a very large star. So, but basically it's very dense, but it doesn't lose much mass. I mean, it does lose its outer layers of gas, but most of the mass would still be there that it had when it ran out of fuel. And it can be different cores. So depending on what kind of fuel the star was able to burn, if it was able to burn right up to iron, it becomes an iron core brown dwarf star, which is denser than the helium core brown dwarf star.
When you had mentioned that it had been denser, I apologize for interrupting. When you had mentioned that it was denser, my automatic assumption was that the mass was greater or would be greater. And it was interesting that you even mentioned that it didn't lose mass, which was completely the opposite of what I was thinking. So I appreciate you verifying that. Okay. Are we going to go from equation 1, or is this where you wanted to start presenting?
I think we should look at equation 1 first.
Okay, yeah.
And actually above that, because, okay, there I explained that when the star collapses into a much smaller size, it rotates faster. And that's to do with conservation of angular momentum. You know, like a skater, if you've ever seen skaters do that, their spins, they usually have their arms out and they curl them in, and that causes them to spin even faster. Okay, so
on roller skates or roller blades. Yeah, I gotcha.
Roller blades or ice skating is the same thing. So if you large, that is, your arms are out, then you will spin slower than if you bring your arms in. You will spin faster. So that means that as the star collapses, its size decreases, so it spins faster. Okay, just like the ice skater. So as it collapses by a factor of 100, it spins at a square of that, because that's what the relationship with angular momentum. That's why if it initially had a magnetic field of 100 Gauss, it ends up with a magnetic field which is 100 squared times 100 Gauss, which is 1 million Gauss.
Wow.
So that, yeah, so it increases a lot, the magnetic field, when these stars form, when white dwarf stars form. And basically, brown dwarf stars will have the same magnetic field. There is a bit of a decrease with time, but I didn't go into that. So again, there is another assumption. I assume there's no decrease in the magnetic field. And obviously, you know, I ignored that. There should be a certain decrease, but I ignored that. But I started out with a standard magnetic field of 100 Gauss. And I explained dwarf stars with much larger magnetic fields, like 1,000 times larger than the standard magnetic field. In Tesla, it's 100 Tesla. Okay, now our sun
actually
that
magnetic field is going to absolutely have an effect on any body that it's close to. And because that goes back into your analogy of the strong force, where it attracts one another.
Yeah, I don't go into the strong force here. I just use the
I know that,
magnetic
but
field.
I was just kind of stepping into that.
Yeah.
That for me, visually, I could understand immediately the natural fluid. What am I trying to say? That was just the next naturally occurring thing to my mind because of the papers that you've put out. That was the first thing I thought. I can't word my freaking thoughts correctly. I hope you understand. Sorry.
Yeah, no, I do understand that. We have to go into the strong force when we realize that there are stars being attracted to the sun. But in this model, I don't mention that at all. I just deal with the magnetic field and the effect it will have on the Earth by heating up the Earth's core. Okay?
Perfect.
So I just wanted to have an idea of what effect the standard kind of brown dwarf star would have on the Earth's mantle, how much of a temperature increase it would create. So that's what you do when you model. You know, you forget about all the other stuff. You focus on one thing. And here I focus on the magnetic field and its effect on the Earth. So then I have to have a magnetic field that changes. And I just say, well, it changes because the brown dwarf star is rotating. And as we know, brown dwarf stars rotate much faster than larger stars for the same reason that the skater spins faster as it decreases in size. So that's to do with angular momentum. So I just give it a simple magnetic field with a periodic change given by the cos function. So I say, well, the magnetic field changes with time. It's got B is the constant strength. C naught is what I'm going to use to vary vary it with distance. And then the cos of omega t is how it varies with time, and it's periodic, because the cos function is like a wave function. It goes up, comes down to the middle, keeps going down, you know, like a wave on the sea. So the C naught is the parameter that takes the distance between the brown dwarf and the Earth into account. And the magnetic field is just 100 Tesla, which I calculated initially that a standard brown dwarf star would have. Omega is the angular velocity or angular frequency of the star's rotation, and that's associated to a period of 27 hours, because I saw there was a brown dwarf star in the Secchi images, and I calculated that its period was about 27 hours by observing how it takes about 27 hours to come back to the same configuration. So I use that here. From that, I calculate the omega, which I need in the B function. So that's the 2 pi over t. The t is 27 hours. So when I calculate...
We need to go back to equation 1.
Okay.
Yeah, scroll up to back to 1. Aren't you explaining equation 1?
Yeah, I was, but it's okay.
Oh, I thought you were actually going to repeat the actual equation itself. You're just kind of giving a...
Okay, I can.
Well, please do that, because I thought that was extremely important. The mathematical side of your presentations, because I don't see anybody else out there making any mathematical equations of any type in this regard, and I want to just have you emphasize that. Thank you. I'll be quiet now.
Oh, okay. That's okay. Thanks for the questions, Chris. All right. So, Scott, you need to scroll up a little bit more so I can look at the equation 1. Okay. Oh, there we are.
It's at the bottom. It'll be a number 1 on the right instead of the left.
Just jumps above.
She put the going down. There you go. It's right there. It's at the very bottom.
There we are. Okay. So B is the constant. It's 100 Tesla. C naught is to take into account, it's a parameter to take into account the distance between the brown dwarf star and the Earth. The cos function is a wave function that makes it vary periodically. Okay?
A cosine, right? Cosine?
It's the cosine function, yes. Okay, and
the
omega,
C naught is the C and the little 0.
Yeah, that's the C naught.
Right. The reason I'm saying this is because I have no friggin' idea what I was looking at. And you actually had to write the equations out for me. And that's how I'm able to present the material. And I'm not afraid to admit that. So I wanted to actually understand what you were saying and how you were